Assalamu alaikum. Welcome back to EE340. In the previous lecture, we talked about EM wave propagation in special media. And the lecture before that, we talked about electromagnetic wave propagation in general media. So in this lecture, we're going to talk about something slightly different. So remember, electromagnetic waves are used to transfer power from one point in space to another. For example, if this one is an antenna, that antenna will transmit an electromagnetic wave. This is the transmitter, this is the receiver. So the antenna will transmit an electromagnetic wave from this point, we call it A, to that point, P. And the receiving antenna will receive that power. So what we want to do here is we want to study the power of electromagnetic waves. So the antenna will transmit an electromagnetic wave. So the antenna will transmit an electric field as well as a magnetic field. Remember that because of the fact that the fields are dynamic, so the existence of one of them requires the existence of the other, and vice versa. So, in order to study the power of electromagnetic waves, we want to, as always and all the time, we should always refer to Maxwell's equation. So in particular, we're interested in this form of Maxwell's equation, or these two equations. So the first one is the well-known Faraday's law. The second one is a modified Ampere's law. So remember, the original formula was something like this. And the heading assumption here is that the medium is linear and isotropic. Similarly, Ampere's law was something like this. And the fact that we have a linear medium and isotropic, which means the epsilon relative, or epsilon as well as a mu, are independent of directions. So the fact that we have both conditions means that B is actually mu times h, D is epsilon times E. So after some mathematical manipulation, I encourage you all to go back to your textbook and read that and follow the derivation. It's very important that you understand how to derive things. So if you follow that, you will see that the last, or the end game, or the last equation, or the equation of interest is this one. So this part, imagine that we have a volume, and a volume like this. So there is a power input to the volume, and there are part of the power, and some power is leaving the volume. So this one is the total power leaving that volume, this part is the rate of change, and this part is the rate of change in the stored electric and magnetic fields. So whenever we have time derivative, we always refer to the rate of change. So the change here is not in terms of increasing the magnetic and the electric field, or the magnetic and the electric energy. It's actually in terms of decreasing those type of energy, those types of energy. And this part is the ohmic losses. So let's go back to the figure here. So the net outward, the net power leaving that volume will be the rate of change in the rate of decrease in the energy stored and in the form of electric and magnetic energy. So those energy will decrease, which means that the energy will be leaving that volume minus the ohmic losses. Remember, we don't have perfect dielectrics, so we have to have a non-zero conductivity. So therefore, the total power will be the total power leaving that volume will be the power supplied, the power originated by or like transferred from being stored electrical energy and magnetic energy, minus the power losses due to the fact that the dielectric is not a perfect one, so the conductivity is not zero here, and that's the Poynting theorem. So the Poynting theorem states that the net power flowing out of a given volume V is equal to the time rate of decrease in the energy stored within that volume minus the ohmic losses. So this integrand is called the Poynting vector. Its direction will be this is a vector, so its direction should be the same as the direction of the flow of the energy. So its direction can be determined using this relation. So now let's derive an expression. Let's derive the expressions for the following quantities. So the first one is the Poynting vector, the instantaneous Poynting vector here. The second one is time average of the Poynting vector. And the third one is the total time average power crossing a surface S. This one is known as, symbolically, this one is written like this. So this one is a vector. This one is a vector as well. This one is scalar. This vector is time dependent. This one is time independent. And this one is time independent as well. So let me go ahead and derive the first one. So imagine that we have an electric field, or like assume that the electric field is along we have one-dimensional electric field. The wave is propagating along the positive z direction, and the electric field has an x component. So the expression for the electric field will be E naught multiplied by the exponent alpha z multiplied by cosine specific angular frequency minus the phase constant multiplied by z, and the direction is along the x direction. Since the wave is propagating along the positive z direction, that means the magnetic field should be like this. So the magnitude of the magnetic field should be the magnitude of the electric field scaled by the intrinsic impedance of the medium scaled by the inverse of the intrinsic impedance of the medium. The attenuation should remain as it is. The oscillation frequency should remain as it is and should be phase shifted by the phase of the intrinsic impedance. And the direction should be along the positive AY direction. So if I take the cross product of those, then I will end up with the following equation. And the direction should be along the positive AC direction. So this equation tells us that the power actually reduced, attenuated, instead of is attenuated by exponential e to the negative 2 alpha z, which is exactly square of the square of the attenuation of the electric and magnetic fields. So in this case, this is actually, let me write it in a better way. This is the instantaneous Poynting vector. So since here we only have a z component, so it's the Poynting vector is written in terms of the z component here. So this is part A. Part B is asking us to find the time average. So if you are given an expression like this, in order to find the time average of that, you need to integrate it over a period. So the time average shouldn't be a function of time. Should be only a function of space, and that should be from 0 to t where t is the period. So this equation actually can be written in the following form. So this one is the phasor form of the electric field multiplied by cross producted with the phasor form of the magnetic field, the complex conjugate of that, the complex conjugate of the phasor form of the magnetic field. So the unit for the Poynting vector is actually watts per meter square. So it's actually energy density. So now we did derive the second one. Let's derive the last one. So if we want to total time, if we want to get the total time average of power crossing a specific surface, we have to do a surface integral of that. So since we're doing the surface integral, the output of that integral, or the result of that integral, shouldn't be a vector, should be a scalar. And that's what we get. So now let's solve one exercise on that subject. So we're given an unmagnetic medium, which means an unmagnetic medium is a medium with a mu relative equals to 1, but epsilon relative may or may not be 1. And we are given the expression for the electric field, and we are asked to find the relative permittivity and the intrinsic impedance. This is the first part. The second part, we are asked to find the time average power carried by that wave. And the last part, we are asked to find the total power crossing 100 centimeters squared of a plane, of the plane 2x plus y equals to 5. So let's solve it step by step. So the first one, so let's find epsilon relative. So remember, beta is omega multiplied by mu times epsilon, which is omega mu relative epsilon relative multiplied by mu naught epsilon naught. So we know mu relative equals to 1. This one is 1 over the 1 over c, where c is the free space speed of light. Therefore, we can write beta as divided by c, and we know beta from this equation is 0.8. Therefore, substituting all the values, omega is 2 pi times 10 to the power 7, c is 3 times 10 to the power 8 meters per second. We end up with square root of epsilon relative is 12 divided by pi, which means epsilon relative is actually 14.59. Now, to find the intrinsic impedance of that medium, we know that the intrinsic impedance of any medium is actually the intrinsic impedance of the free space divided by the intrinsic multiplied by epsilon relative and multiplied by the square root of epsilon relative over mu relative over epsilon relative. Actually, this one for lossless dielectric, this expression for lossless dielectric. So we know that this one is a lossless dielectric because there is no exponential part here, so there is no attenuation. So this one should be along x. So in order to get 1, alpha should be 0. So it's a lossless dielectric. Therefore, if we substitute, we will end up with 120 pi divided by pi multiplied by 12, which is actually 12 12 pi, which is 98.7 ohms. So now we solve part A. To solve part B, we can integrate, we can find the instantaneous, there are two ways actually. The first one is to find the instantaneous Poynting vector, and that's what we're going to do, and from that we can find the time average. The second one is we need to actually find the electric field, the magnetic field, and we have enough information to find that, and we can use this equation to solve for that. Let's find the instantaneous Poynting vector here. Since we have sine on both sides, so this one can be simplified to sine squared omega t minus beta x, and the direction should be along the positive ax direction. So we need to integrate that over a period to get the average. So 1 over t, 0 to t, and that's going to give us, there is a unit vector here, and that's going to give us a squared divided by 2. If you do the integral over one period, this one, you can use the square formula, which is 1/2 minus sine 2 omega t minus 2 sine 2 omega t minus 2 beta x. And if you integrate a sine function over an integer multiple of period, then that integral will be 0. So all what you're left with is the first part, which is 1/2. So if you integrate this part from 0 to t, then you will get 1/2 times t, and since we're dividing by t here, so t will cancel the other t, and we will end up with this formula here. We can substitute the values for squared 2 times 98.7 ax, and that's going to be 81 ax. The unit is milliwatt per meter squared. Now we want to find the total power crossing the volume, crossing 100 centimeter square of plane 2x plus y equals to 5. So we want to solve actually this integral. So in order to find the differential surface, or in order to find the unit normal, we need, in order to solve this integral, we need to find the unit normal of the surface. So to find the unit normal, we need to take the gradient of that one, of this equation, which is 2ax plus ay divided by the length of that vector. And this is the normal direction. So since the average power is not a function of any spatial component here, so I can take it as a constant. Started with this one, and I know the unit vector here. I know the surface area, so this one will look like the following. So this one is 100 centimeters squared. So to solve that one, let me have another page here. So I know the magnitude of that, which is 81 milliwatts per meter squared. The surface area that we are interested in is 100 centimeter squared, so I need to convert it back into meter squared. And I have this unit vector, so the contribution of the y component is nothing, since I'm using the dot product. So I will end up with power average is 724.5 microwatts. Okay, thank you very much. In the next lecture, we're going to talk about the wave, when wave actually goes between two means.